Hi, and welcome back to the channel. Previously, we talked about Databricks' Delta Lake and what it is at a very high level. Link in the top right-hand corner. You do need to make sure you understand these basics before proceeding here. Today, we'll be doing a deep dive into ACID transactions, a data quality feature in Delta Lake. So as always, let's lay out the objectives. It will be a drill down of Delta Lake's ACID transactions, a gold standard for database reliability. The acronym ACID stands for Atomicity, Consistency, Isolation, and Durability. We will outline the problem each of these properties solve, as well as how they actually work under the hood. I will then take you through a sample PySpark script to demonstrate how these properties work in action. Finally, I will give a short summary and outline the next Delta Lake feature video coming up for the channel. So let's look at ACID transactions. ACID being the acronym for those four properties that ensure a high standard of data quality in Delta Lake. The secret quality source of Databricks Delta Lake, if you will. For a long time, big data, namely the data lake, meant sacrificing reliability for scale. If a Hadoop job crashed halfway, for example, you had a mess. The creation of the open source Delta Lake changed that by bringing in ACID transactions, the gold standard for database reliability to the Cloud Object Store. As engineers, understanding this is vital because it determines how you handle job failures, concurrent writes, and data integrity. From a data architecture perspective, you want to know how all this works in detail and is it reliable or not. So let's first look at the A in ACID, atomicity, or the all or nothing rule. Imagine you have a financial transfer where you've debited the sender, but the receiver's update crashed. Without atomicity, money vanishes. In the Delta Lake, we use a transaction log. So no matter how many files Spark writes to S3 or ADLS, um, they don't exist in the table until a JSON entry is added to the _delta_log folder that we talked about previously. This saves you from having to write complex cleanup scripts, for example, after every failed production run. So let's look at a further example, and the one on the screen here. So imagine in a standard data lake, a Spark job writing 1,000 files crashes at file 500, and you're left with 500 partial records. Downstream jobs read this zombie data, leading to incorrect reports, which we don't want. The Delta solution is atomicity. And the key mechanism for atomicity is the transaction log, which acts as a single source of truth for the table state. So let's go through the stages of that life cycle. Before the commit, so a writer starts a transaction with, say, for example, an update statement. It writes the new data files in Parquet format to the data directory, but these are not yet considered part of the table. During the commit, a writer attempts to write a newly sequentially numbered JSON commit file to the delta_log table. It's then a success or failure scenario due to the atomic file writes in cloud storage. The JSON file either appears completely or not at all. If the write is successful, the transaction is committed and the changes become visible to the new readers. If the operation fails mid-write, no partial commit is visible and the uncommitted data files are ignored, eventually cleaned up by the vacuum operation, which we'll touch on in a later channel video. Result is readers always look at the latest complete JSON commit file or checkpoint to determine the current consistent state of the table. So in short, transactions are committed to that _delta_log folder only when the entire job succeeds. If it fails, partial files stay on disk but are not seen by data readers. It's if the failure never happened. So next is the C in ACID, consistency. Now you'll see there's a slight overlap with atomicity, but hopefully become clear in the stages. Consistency ensures that your data follows the rules you've set, essentially. Uh, in a standard data lake, you have schema on read, which is just a fancy way of saying hope for the best when you query. In contrast, Delta Lake gives you schema on write. So if a source system changes its format without telling you, Delta will stop the pipeline immediately rather than letting corrupted data flow into your silver or gold layer. So let's look at the example here. Without table field constraints, an age column might accidentally receive a string unknown or a negative number, breaking your machine learning models or dashboard aggregations downstream. Um, the Delta Lake solution enforces schema on write and checks constraints. So the system ensures that the table moves from one valid state to another, essentially. If a record violates a rule, the whole transaction is aborted. So let's go through the steps quickly. So starting a transaction. So that's usually by reading the latest version of the table from the transaction log to establish a baseline snapshot. Then we validate the data in the schema. So the incoming data is validated against the current table schema and any defined constraints. So that age, for example, has to be greater than 0, for example, or unique email addresses. Then the new or updated data is written to a new Parquet data files in the underlying storage, so in S3, for example. But these files are not yet part of the active table. And this is where the atomicity similarities come in, that the attempt to commit, so a newly sequential commit entry, so that JSON file is, for example, is generated for the delta underscore log directory. That this entry records the actions, so which files to add, which to logically remove, and any metadata changes. Then there's the atomic log write, which is the commit file is written to the cloud storage using an atomic operation that we discussed earlier. This is the crucial step. The file either completely succeeds or completely fails. And then there's a further conflict check. So before the commit is completely finalized, the Delta Lake checks if any other transaction modified the data since the initial read in step 1. So if the conflict is detected, the current transaction is rolled back and the process may retry with the latest table version. Then there's that transaction finally to the final valid state. If the commit is successful, that transaction log, the secret source in that transaction log is updated. The table version increments and the new data files immediately become visible as the latest consistent snapshot of the table. The table has moved from one valid state, like I said, to another. And then finally, there's a rollback on failure feature. So if any part of the transaction fails before the commit is finalized, so for example, a power outage, the partial data files remain untracked and later cleaned up by the vacuum command, ensuring the table remains in its previous valid state. Isolation, the I in ACID. Isolation is about handling multiple users. Delta Lake uses snapshot isolation. This means a reader sees a consistent snapshot of data from the moment that they start the query, even if someone is currently writing the new data. You'll never get a file not found error, for example, just because a background process is vacuuming or overriding the table. So let's look at this problem on the slide here. Two people are trying to update the same table at once. User A deletes some rows while user B adds them. In a normal file system, they might overwrite each other's files potentially losing data. Now, the Delta Lake solution uses optimistic concurrency control, or OCC. It assumes that conflicts are rare, and it validates changes at commit time. If a conflict has occurred, one user is asked to retry, ensuring a serializable isolation. So once again, let's just drill down into the steps so we understand it. So as always, transaction begins. It reads the latest available version of the table from the transaction log. This ensures that the operator, starts with a consistent, isolated snapshot of the data, obviously. Then we perform the operation. So the transaction executes its logic, filtering or modifying on its isolated snapshot. At this point, it has not yet written anything permanent to the table. Then, before committing, the transaction prepares a proposed commit. So a series of actions like adding or removing data files. It then checks the transaction log for any new commits that have occurred since that first step, since that reading the transactions or reading that file. This is the core of conflict detection. Then we have a validation step. So Delta Lake validates if any of those concurrent changes happening will affect the current will affect the data the current transaction is reading or modifying. So, for example, if transaction 1 modifies, say, row A and B, and transaction 2 modifies row B, transaction 2's commit will fail because there's a conflicting write with that row B between those read and write steps. Next is that success or failure decision. So if there are no conflicts, it's easy. Its transaction is marked as successful. If the proposed commit is atomically appended to the transaction file as the next version of the file, making the changes immediate, visible to future transactions. But on the other hand, if there is a conflict detected, like this scenario, the transaction fails and is typically retried by the application or the Delta Lake engine. This failure ensures that the database state remains consistent and correct. So to sum up, there are two distinct types of isolation levels that the Delta Lake guarantees. One is for write operations called serializable isolation. This is the strongest isolation level. Delta Lake guarantees that the results of several concurrent writes is the same as if those writes had happened one after the other in some serial order. The conflict detection previously enforces this. For read operations, you've got snapshot isolation. So read queries operate always on a consistent snapshot of the table from a specific point in time, ensuring they're never exposed to partial or inconsistent data. They are isolated from any writes that occur while the read is running. So by combining the transaction log with this optimistic concurrency control, or OCC, Delta Lake ensures data integrity and consistency even under heavy concurrent workloads. And finally, durability, which is the promise that, or property that once the system says success, that the data is committed to non-volatile storage. So since Delta writes to highly available cloud storage like S3 or Azure Data Lake storage, for example, and the transaction log in itself is stored there, we inherit massive durability of those cloud providers. So let's look at this problem scenario to demonstrate durability. In many distributed systems, a successful write might still be lost if a specific node or a caching layer fails. before the data hits the physical disk. The Delta Lake solution is that once a transaction is committed to that transaction log, or that _delta_log folder on the cloud object store, it is guaranteed to be permanent. Even if the entire Databricks cluster vanishes a millisecond later, your data is safe. So let's go through the steps and see how this materializes. So firstly, let's give the example of data writing. So a write operation begins, so like a merge or insert, creating new Parquet data files and potentially modifying existing ones. Then we have a transaction log write. Before the operation is visible, metadata about these new files, which files were added or removed, is written as a new JSON file, a commit to the _delta_log directory. Then as before, that the commit process is always atomic. Either all metadata gets written, making the transaction durable and visible, or none of it does, leaving the table state unchanged. So there's that all or nothing rule again. Then, of course, we have that data file persistence. The actual Parquet data files stored in cloud storage or like S3 are written independently. So if a crash happens after the log commit, but before the file writes finish, the log, which says the file should exist, will still point to the latest valid state. And this, on restart, the Delta Lake reads the log, if there's an issue, to reconstruct the current table state. If a partial write occurred, the log ensures only completed transactions are recognized, preventing data corruption and allowing you to revert to older, consistent states, which we will discuss a bit more in a further video. It's the concept of time travel. This robust logging and atomic commits ensures that your data lake operations are as reliable as database transactions, preventing data loss and corruptions, which is one of the downfalls of just having a data lake by itself. Okay, so let's jump into a demo in Databricks to show ACID transactions in action. I will explain the code a little bit as I go along, and any shortcomings to replicate it. But all you have to do is follow along and reference what you've just learned. Okay, so I have the Databricks free edition open. Using this one, so if someone else wants to replicate it, they can. There are a number of restrictions on the free edition, but I think we can get there. So I've created a notebook, and I'm just going to go through each of those ACID properties that we discussed earlier. I might just, let's have a look here. I've got this PySpark script, and I might just run it and start to explain it. Might be the easiest thing to do while we're waiting. So so we've just got an initial setup area. So I'm just calling a few functions from the library, and I'm creating just defining a table name. It has to, because there are restrictions with the DBFS root, I need to use a managed table. So this is just defining the table name, and then I'm just making sure that there are no other tables with the same name are existing. So if they are, just drop them just from previous runs. Then I'm actually creating the data set. So adding a data set of 10 rows and a column called data, and just populating it with initial, the literal initial, and just writing that as a managed table. It will by default add an ID as well. So it'll be ID and data. Then just as a sanity check, all I'm doing is returning the first 5 rows. So let's just have a quick look at that. And there we go. So we've just got ID and data, and yeah, it's not in 1, 2, 3, 4, 5, 6, 7. I've run it a number of times, and it's but it is sequential anyway. Okay, so let's get into it. After the initial setup, let's look at atomicity. So atomicity is that all or nothing rule. So we're trying to verify that partial writes are not possible. So we're going to simulate a crash essentially. Um, Firstly, just in the output, I'm printing out the initial count, which should be 10. And then what I'm doing is I've just got this try catch block where I am trying to simulate a crash here. So I'm adding an extra 20 rows to data. And when the column ID is greater than 15, then I'll be raising an error. So I want to make sure that, up to that 15 ID feet, well, I haven't got any extra rows. So, and then it's got an append, trying to append it here. This shouldn't append. If it's all working well, then I'll get that, print that exception, and then I'll do another count, and I should get 10 rows still. So let's just double check that. So okay, initial row count is 10. A system crash mid-write. That's as expected. So hit that exception block, and then we double check to make sure there wasn't a partial write of that append attempt, and there wasn't, so it's all good. Count is still 10. All right, so next is consistency, and if you can remember, consistency is about like the rules, like schema enforcement, table constraints, field constraints. We had the example of the age column in our presentation, but let's look at an attempt to write some data and change the schema at the same time. So by default, you shouldn't be able to do that in Delta Lake. So here we go. We're using .print schema, which is going to display our metadata of our columns, and then just in this try block, we've got a bad data frame, creating a data frame here with an extra column called extra underscore info, and trying to add this row here. And then we're displaying, what the actual the metadata, the table metadata there from that print schema, and then we'll attempt to write this or append it to the table. We should get an exception, and then we'll just check the schema again to make sure nothing was broken. There is a merged schema, and you can set it to true, but that's not for this presentation. We just by what's out of the box, what is the default, and it shouldn't allow you to, add a column on the fly. So you need that structural integrity and that consistency. So my mouse is a bit funny, but I'll keep going. Consistency. All right, so that's the initial table schema with ID and data. This is the one with the extra column that they're trying to, and we're simulating that crash there. That's the schema attempt, and there we go. Delta Lake blocked that invalid schema. Then we double check the schema again, and we've still got that ID and data, so it's all good. Schema is unchanged. Next one is isolation. So yeah, with this particular example, I'm using snapshot isolation. So I am, that's to do with readers of the data not being affected by underlying writes that are happening at the same time. So that concurrency going on. So there is sequential isolation that we discussed. So that's multiple writes at the same time, which is quite difficult to replicate. So this is more a snapshot of the data. So so as per what we've done before, we get a count of the table name, and then we're going to look at. We're just going to go in. This is really this data frame. It's going into the transaction log and looking at the history and the versions of the data, and then just picking up the first one, and we're just assigning the starting version to that, which is 0, which would be that create table script that'll be in the transaction log as version 0, and then we're going to delete the data from that table, and then double checking with the print statement what the live count is, it should be 0. So up here we've got 10, and then we delete the data, obviously, and then we've got 0. So to sort of replicate the isolation part, and just use your imagination, but we've got this, and this goes into a bit of versioning and something we're going to discuss a bit later, which is time travel. But what we're doing here is we're checking that the read that they're reading at the moment, which is version 0, they'll be able to see it and query it. So version as of. So this is looking at the starting version. So with that, we should be able to get a count of 10. So it's just a little bit of like trickery there, but it's saying that snapshots are isolated. So there's, even though you delete the data, the reader is unaffected, essentially. So let's just have a look at the output. Okay, so isolation here, initial count of 10. We get that the snapshot version, which is version 0, and then we do a delete of the data, check the count, it's 0, and then it's like a simulation of the reader, what he's seeing, because we can go to the previous, stick on that previous version 0, and that's the initial one, which is 10. So they're unaffected by delete in the background. There's no horrible error coming through. And last but not least is durability. So let's have a look here. Durability, okay. So it sort of blends in a little bit to the isolation, and do a little bit with versioning with this one. But it proves that, like here, as we're saying here, is that the truth exists in the metadata. So in that transaction log, it's immutable in that JSON log, in that delta_log_ folder on the disk. So no matter what changes happen, the data persists, and once you've committed a transaction, that data and the metadata persists. So let's just step through. So we've got a data frame here where we're getting all the metadata. That's all that describing detail does, all the metadata available and displaying it in a data frame. And then we're just making sure what format the table is in, which is a delta managed table. Then what we're doing is we're grabbing the last 3 transactions. So and then selecting various parameters in those last 3 transactions. So we can just get an idea that the durability, like it says here, is confirmed via the transaction history. So even though right now the current, the current, we deleted that data, that should come through in the transaction log, and we can just basically it's recoverable. So version 0, that is that initial create table, and then we had that delete when we've run that run the PySpark script. So there's a lot of information here that we can see that it's it's a managed table. So is managed equals true, and then we've got all the files removed when we deleted it, created it with that data set of output rows equals 10. We've got all the data here. We can't see the locations with the free version of the actual Parquet, but yeah, it's definitely there. It's definitely recoverable, that we'll talk about a bit later with time travel. So thank you for staying the distance. To summarize, we explained why ACID properties are so fundamentally ingrained in Delta Lake. We dove deep into not just what each of the properties solve for data quality, but also the steps in each execution cycle. And finally, we had a demo showing ACID transaction features in action in the Databricks tool itself. In the next video, we'll tackle time travel, a natural follow-on from our durability discussion. So please stay tuned. Thank you.